Hi everyone. In this video I will demonstrate how you can perform binary logistic regression using R. Topics include use of the GLM function, running analyses that include continuous and factor variables as predictors, how to obtain confidence interval results for regression coefficients and odds ratios, how to obtain likelihood ratio test results, and how to obtain pseudo R-square results. Links to the data in CSV format and a text file containing syntax associated with this demonstration will be provided for you underneath the video description. I will also provide a link to this PowerPoint as well, which will contain additional information on interpretation of the results. So if you find the video and materials I've made useful, please take time to like the video and share it with others, and also please consider subscribing to my YouTube channel. Now, before we get started, let me also say that you will need to have the DESC tools package and manipulate package installed in order to obtain some of the results that I cover in this video. So make sure that you've done that before we get started. So now let's move on to our example. So in this example, we are attempting to model the likelihood of early termination from counseling in a sample of 45 clients at a community mental health center. The dependent variable in the model is terminate, which is coded 0 for did not terminate early, 1 for terminated early, where the did not terminate early group is the reference category and the terminated early group is the target category. Two predictors in the model are categorical. We're going to have gender identification, which is coded 0 for male, 1 for female, with male being the reference category, and income, which is an ordinal variable coded 1 for low, 2 for medium, and 3 for high. The reference category for that variable is the low income group. Finally, two predictors will be treated as continuous in the model: avoidance of disclosure and symptom severity. Now, as I noted before, the data is contained in a CSV file. So the first column contains the subject identifier. We have terminate variable, avoidance of disclosure, symptom severity, gender ID, and income. And what we're going to need to do is to import this into R. So what I'm going to do is open up R right here, and the first thing I have to do is actually point R to the directory that contains the data. So I'm going to go down to change directory and make sure it's clicked on downloads. That's where the data is actually contained. I'm going to click on OK, and now we're going to use a little bit of code just to import the data. So I'm going to create a data frame that I'm going to call LR data. Then I'm going to type in an arrow right here, and then I'm going to type in read.csv because the data is in a CSV file, begin quotes, and then the name of the data file. So I'm going to type in binary space logistic space regression space terminate .csv in quotation marks. Then I'm going to type a comma and then header equals true, and then go to the next line and I'm going to type in SCP equals, and then we have quotation marks, comma, and in quotation marks. So this is just indicating that we're reading a comma separated file in. So next I'll hit enter, and let's take a quick look at our data using the structure function. So we'll just type in str, and then inside parentheses here we'll type in the name of our data frame, which is LR data. So you can see this is it. You can see that we have our terminate variable right here, avoidance of disclosure, symptom severity, gender ID, and income. You'll also notice that R read all of these variables in directly as integers. So now let's begin with a simple model where we are just going to predict the terminate variable or terminate outcome as a function of our two continuous variables. So what I'm going to do is create essentially a fit object that I'm just going to call fit, so it's arbitrarily named. You can see we have our arrow that's typed in, and then we'll type in GLM. So we're going to be using the GLM function, and this will allow us to run our binomial logistic regression. So we'll type parenthesis, and then we'll type in the name of our dependent variable, which is terminate. We'll follow that up with a tilde sign and then the names that are appearing in our data frame as well for our predictors. So make sure that when you're typing in the names that they are matching what's in the data frame. So I have terminate, then I've got avoidance of disclosure, which is spelled out here, AVDISCL right there, then plus, then symptom severity, which I'm going to type in SYMPSEV. All right, so now I'm going to type a comma in and then use the data argument in order to specify the data frame. So we're going to type in data equals LR data. And then finally, following a comma, we're going to type in family equals, and then in quotation marks, binomial, in quotation marks, and then in parenthesis. So we'll hit enter, and then we'll type in summary. So we're going to use the summary function, and then fit, and we have our output. So basically, as you're looking at your code, the GLM right here, this is basically running the model, and then we're storing that information in an object that is called fit. And so when we use the summary function, now we get our output. So you'll see down here under coefficients, we've got our regression coefficient estimates, our standard errors, z-values, and then p-values that are given right here. You'll see that we have the avoidance of disclosure variable, and there's a positive coefficient right here, and you also see that it's statistically significant. So given that this coefficient is positive, this is indicating that individuals who are scoring higher on avoidance of disclosure were more likely to terminate early than those who scored lower on avoidance of disclosure. The symptom severity variable, you can see there's a negative coefficient right here indicating that individuals who scored higher in terms of symptom severity were less likely to terminate early than those who scored lower on symptom severity. Okay, so now let's run our analysis, but using our categorical variables, which we had gender identification and income. So what I'm going to do is I'm going to create a new fit object. I'm just going to basically save over the old one. I'm going to call this fit, type in my little arrow right there, and then we'll type in GLM, and then inside the parenthesis again, terminate, tilde, and then the names of our predictor variables. So let me just kind of note that whenever you're typing in GLM, the first argument right here should be, or the first variable that appears is the name of the dependent variable, tilde, and then on to the right are the names of the independent variables, or the predictor variables. So now what we're going to do is we're going to type in avoidance of disclosure first, so AVDISCL, plus symptom severity, so SYMPSEV, plus, and now we want R to recognize gender identification as a factor. Now remember, in the data frame, R is treating the gender identification and the income variables as integer variables. So we want them to we want the program to treat them as factors, so they'll go ahead and perform the dummy coding for us. So what we'll do is we'll type in factor, and then inside parenthesis gender ID, and then plus factor, and then inside parenthesis income, in parenthesis, and now we'll type in we'll type a comma. Go to the next line, we'll type in data equals, and then the name of our data frame, which is LR data, and then comma, family equals, and then inside quotation marks, binomial, in quotation marks, in parenthesis. So now what we can do is we can hit enter, and the analysis has been run, and the data is saved underneath the fit object. So now I'm just going to type in summary and fit inside parenthesis, and there we see our results. So now you can see right here again there's avoidance of disclosure and symptom severity. Down here we have gender ID, and it's basically being treated as a factor variable. Then we have income and income right here, and you'll see a 2 and a 3 right here. And basically these are dummy variables. So the 2 is essentially associated with the medium income group, the 3 is associated with the high income group. And what each of these coefficients are right here are comparisons between either the medium or the high income groups versus the low income group. So looking at our coefficients right here for avoidance of disclosure, you can see there's still a positive coefficient and it's statistically significant. So essentially individuals who scored higher on avoidance of disclosure were predicted to terminate earlier than those individuals who were lower in avoidance of disclosure. We still have our negative coefficient for symptom severity, and it's statistically significant, indicating that individuals scoring higher on symptom severity were essentially less likely to terminate early than those who were low on symptom severity. Now with our gender ID variable, remember it was coded 0 for male and 1 for female. So this negative coefficient right here would indicate that females were less likely to terminate earlier than males, but that coefficient was not statistically significant. Then with respect to our two dummy variables for income, you have a negative coefficient here and a negative coefficient here, and those would basically indicate that individuals who were at medium income were less likely to terminate earlier than those individuals who were low income, and those individuals who were higher in income were less likely to terminate early than those who were low in income. But both of those coefficients were not statistically significant. Okay, so now let's say that we want to generate confidence intervals for the regression slopes. So we can do this by just typing in the following. We'll type in CONFINT dot default, and then inside the parenthesis the name of our fit object. So now we have the confidence intervals associated with each of our regression coefficients. If we want to generate odds ratios, we can also do that pretty easily. So we can do that by typing in EXP, and then inside parenthesis COEF, and inside another parenthesis fit, in parenthesis, and then close out the other parenthesis, hit enter, and so now you can see that we have the odds ratios associated with each of our predictors. And essentially, for our example, the odds ratio would indicate the multiplicative change in odds of early termination for every 1 unit increase on a predictor variable. Now, if you want to obtain confidence intervals for the odds ratios, you can do the following. So what we'll do is we'll type in EXP, inside parenthesis we'll type in CBind, inside another parenthesis we'll type in OR equals COEF, and inside parenthesis fit. And so all of this is inside in that text file that I was referring to earlier. So if it's a little hard to follow, you can just download that and follow along because it's there. So next we'll type in we'll have only one in parenthesis there, excuse me. We'll type in comma and then CONFINT dot default, and then inside parenthesis fit, in parenthesis, and another in parenthesis, and when we hit enter, you can see that now we have a column containing odds ratios and the lower and upper bound of the 95% confidence intervals. Now, unlike the 95% confidence intervals associated with our original regression coefficients, where basically the null is 0, the null in the case of the odds ratios is 1, or rather a value of 1. Now, typically when it comes to running and interpreting a logistic regression, typically you would start by looking at evaluating the overall model fit and then proceed to the regression coefficient. So I'm kind of doing this a little bit backwards from how you would ordinarily do this. But one of the things that you might do when it comes to testing the overall model fit is to compare the model containing the full set of predictors against a null model, or basically an intercept-only model. So to do this, what we're going to do is perform a likelihood ratio chi-square test. Now, we've already run our model and obtained indicators of fit where we have our full set of predictor variables. So what we need to do in order to perform this test is to generate statistics from a null model. So to do this, what I'm going to do is I'm going to create a new fit object. I'm going to call it fit and then null, and then type in my little arrow here, type in GLM. Inside parenthesis, I'm going to type in the name of the dependent variable, which is terminate, then tilde, and then just a 1. So we're not going to add any predictors. So this is just basically going to be an intercept-only model. I'll type a comma, then data equals LR data, and then family, again, is going to be set to binomial. And remember, that's going to be in quotation marks. So we'll hit enter, and then summary, fit null, just to take a quick look, and you can see this is our intercept only model. So you can see right here we just have our intercept that's given as well as the estimate and so forth. So to test whether our full model containing our predictors represents a significant improvement in fit over the null model, we can use the ANOVA function. So I'm going to type in ANOVA, and then inside parenthesis I'm going to type in fit null, so that's the name of our object containing the null model, then comma, then I'm going to type in fit, which is basically the object that's containing our results from the complete model. Then I'm going to type in test equals, and inside quotation marks LRT, in quotation marks, in parenthesis. And so now you can see that we have right here you've got model 1 and then model 2 that's given, and model 2 is basically our complete model with all of our predictors. So down here you've got deviant statistic. This is distributed as chi-square, and then we have basically our p-value. And as you can see right here, the results indicate that our full model containing the complete set of predictors represents a significant improvement in fit over the null model. Now, another way in which we could evaluate overall fit of a model is to look at pseudo R-square values. So these are basically loose analogies to the OLS R-square that we're commonly used to. They're actually not computed in the same way, and there's a lot of ambiguity in terms of how to make sense out of them. But if you want to report on these, there is a way to do this. One way is we're going to use our library function, and we're going to call up the DESC tools package that I mentioned earlier that you probably needed to install. So now what we'll do is we'll hit enter, and so now that package has been activated. And the function that we are going to use is called pseudo R-square. So I'm going to type in capital P, then pseudo, then capital R2 right here. Inside parenthesis, we're going to type in the name of our fit object that contains our model results. So I'm going to type in fit right here, comma, and then we can basically type in which equals, and then a C, and inside parenthesis, we're going to type in the names of various pseudo R-square names. So first off, we're going to type in McFadden. So capital M, lowercase c, then capital F, and then Fadden right here, in quotation marks, comma, and then we're going to do the same but obtain an adjusted McFadden's. So we're going to type in McFadden, and then A, D, J, capital A, then a D and a J, in quotation marks, comma. Then we'll type in Nagel-Kirky. This is another common one. So Nagel-Kirky. There's an in quotation marks there. And then we'll type in new quotation marks in Cox, and then Snell. And the C and the S are both in caps, in quotation marks, and then two in parentheses here. And so now you can see that we have our pseudo R-square values that are given. Now there is another approach that you can use to compute an R-square value that's much more consistent with how we think about R-square in the context of least squares regression. So specifically what we're going to do is to generate the square of a correlation between the predicted probabilities associated with group membership and the group membership variable itself. Now what I've done is actually opened up the text file that I had mentioned earlier, because I'm going to walk you through different pieces of this here. So first off, you'll notice right here that I'm taking the LR data, the name of my data frame, and I'm going to modify it. So I'm basically using the data.frame function right here. You'll see I'm typed in the name of the original data frame name, then a comma, and then this is the name of the first variable that I'm going to add to this data frame. I'm going to call this basically predicted logit. So but it's spelled P-R-E-D-L-O-G-I-T. So it's an arbitrary name, but that's what I'm using. Then I have equals, and then predict, and then inside parenthesis I'm typed in the name of the fit object, which I'm calling fit. Then you can see I've got basically the in parentheses that are given over here. So that is going to generate a column in my data set, basically my data frame of predicted logits. Then next I'm going to add predicted odds. So basically odds are essentially created by exponentiating the logits. So here in this next section I'm again kind of modifying the LR data frame by now adding in predicted odds. So we have right here predicted odds is equal to, and you'll see it says EXP for exponentiate. Then basically we're exponentiating this right here. So you can see that's where it's appearing next. Then finally we have, we're modifying the data frame again by adding predicted probabilities. So the predicted probability variable that I'm adding right here is equal to, and you'll see right here it's got LR data, then a $, then predicted odds. And so basically it's going to be the predicted odds that are generated right here. So at this step right here, we're going to basically have a new LR data frame with this predicted odds variable. And so right here it's basically saying locate the predicted odds variable contained in the data frame. Then you'll see there's a division sign, basically a backslash, and then inside parenthesis 1 plus LR data $ predicted odds. So that's basically how we're going to add predicted logits, predicted odds, and predicted probabilities to our data frame. So what I'm going to do is actually just I'm going to copy all of this and paste it into R. So otherwise there would be a lot of typing to do. And I'm going to type in str for the structure function, then LR data. And so now you can see that we have the predicted logits, predicted odds, and predicted probabilities that have been generated. So now our data frame contains the predicted probabilities and also the grouping variable, which is terminate. So now we can just use the core function in order to generate the correlation between those two variables. Then following that, we can square it. So what you'll see right here is R. I'm just creating a new data object, which I'm calling R, which is going to contain the correlation coefficient generated by correlating predicted probability and the terminate variables. Now you'll notice too that we've got LR data $, and then the name of our variable, which is predicted probability. So this is indicating that we have to basically indicate the data frame name followed by the $, and then that is indicating, and then we have the name of our variable predicted probability and then terminate over here. So I'm going to correlate, basically copy this and paste it in as well, hit enter, and then if I type in R right here, you can see the correlation between the predicted probabilities and the terminate variable is 0.729. So basically to obtain the R² value, we can just type in next, we'll type in R and then a caret and then a 2, and there it is. So basically it's 0.53. So we can say that the predicted probability and terminate variables share approximately 53% common variation. Okay, so the last thing that I want to show you in this video are how to use likelihood ratio tests in order to test each predictor. So in the results that I went over previously, basically the results were given as walled z-tests. So in this case, we're going to use likelihood ratio tests in order to test the model coefficients. Now to do this, it takes a little bit of work. So first off, you'll notice that I'm going to start off with the full model. So you can see right here we have our fit object with all of our predictors that are included. So essentially the likelihood ratio test for each of the individual predictors involves taking the full model and removing one of the predictors. And so the basic idea is that if the fit, the decrease in fit as a result of removing a predictor is statistically significant, then that would be an indication that the predictor is a significant contributor to the model. So the first demonstration I'm going to use is right here, where we're going to be testing the avoidance of disclosure variable to see if it is a significant contributor to the model. So to do this, I'm creating another fit object that I'm just going to call fit2. So here we've got our GLM function right here, again the name of our dependent variable tilde, and then the names of all of our predictors, but not including the avoidance of disclosure variable, and then all the remaining syntax is exactly the same. So when we run that analysis, we can use next the ANOVA function, and we'll have the fit object first in this position right here. We've got fit and then comma fit2, and then we're going to perform the likelihood ratio test right here. So just to kind of make this quick and easy, I'm just going to copy all of this and go into R right here and paste it in and hit enter. And so right here you can see that the deviance for the first model containing the full set of predictors is smaller than the deviance for the second model where we removed the avoidance of disclosure variable. And basically the model with the lower deviance is presumably fitting better. So you can see we have a decrease in fit as a result of removing avoidance of disclosure, and you can see right here that that change in fit is statistically significant. Okay, so now let's look at another model. We're going to create fit 3 where we remove the symptom severity variable, and then we'll test it in relation to the full model. So again, I'm just going to copy all of this and paste it in to save a little bit of time. And so now you can see the fit of the full model again. So you can see it's exactly the same as what we had before. And then here's the deviance for our reduced model without the symptom severity variable, and you can see that it's greater than the complete model, and you can see that there is a significant change in fit. So basically, again, the symptom severity variable, when we removed it, we can see a significant worsening in fit relative to the full model. Now let's rerun our analysis, and we'll generate a fit 4 and a fit 5 variable where we are excluding either income or gender, and we'll look at the model comparisons. So I'm going to copy those and paste it in as well, hit enter. And so for model 4, where we basically removed the income variable, so that's our model 2 right here, where you can see there's no income variable that's given. You can see that there's a slight worsening in fit looking at comparing the deviances from the full model and the reduced model, but you can see that there's not a significant decrease in fit as a result of removing the income variable. So income would not be considered as a significant contributor to the model. For the next one, where we are removing the gender ID variable, leaving only avoidance of disclosure, symptom severity, and income. In this case, you can also see, based on the deviance value for the reduced model, it's still greater than our full model, but you can see right here that the change in fit is not statistically significant. Okay, so that pretty much concludes this video demonstration. As I mentioned before, the data and that text file that I was referencing are available for download underneath the video description, so be sure to check them out. And this PowerPoint, there's actually a lot that I kind of go into here, so you can also download that as well, so be sure to check those out. And if you find the video materials useful, please take time to like the video and share it with others. And again, please consider subscribing to my YouTube channel. Thanks for watching.